So far, we have discussed quantum circuits, qubits, and some basic gate manipulations. Now, let's turn to the quantum Fourier transform. We'll start with the classical discrete Fourier transform, abbreviated DFT. This takes a vector of complex values in some sort of real space, for instance time, into a vector of complex values into some Fourier space, for instance frequency. The DFT is defined by this formula. Don't worry if the DFT is not familiar to you. The quantum Fourier transform, abbreviated QFT, is very similar to the DFT, and I'll hopefully be providing enough intuition behind the QFT so that we don't need to know about the DFT at all. The quantum Fourier transform is in effect an implementation of the DFT, where we take the normal computational basis states 0 up to n minus 1 into a Fourier basis 0 up to n minus 1, here denoted with a tilde. However, remember that we always measure in the computational basis, that is, the untilted version. So we want to express these Fourier basis states in terms of a linear combination of the original basis. This relation is precisely given by the discrete Fourier transform and is presented here. For an arbitrary input state, we would get this instead, where we have simply substituted in the basis transform. Note how the QFT acts upon the complex amplitudes of a quantum state, and is also just a unitary transform between the normal computational basis and a Fourier basis. Before we get too deep into the maths, let's try to get an intuition for this basis transformation. A nice way of visualizing the QFT is by looking at what the normal basis states get mapped to in the Fourier basis. We can do so by simply just thinking about what happens when we count in the computational basis. So with 4 qubits, for instance, the decimal 0 is just 0000 across our 4 qubits. In the Fourier basis, 0 tilde has all the qubits pointing to the plus state. But let's see what happens when we go to decimal 1, which is 1000 in our qubits. The Fourier basis states have just all rotated about the z-axis. Also, each qubit rotates by an amount that appears to follow a pattern. The first qubit by 1/16 of a turn, the second one by 1/8, the third by 1/4, and the fourth by 1/2. Replay the video to see this for yourself. Let's see what happens if we continue counting upwards. Let's go to 2 tilde. Once again, the first qubit has rotated by another 1/16, the second by an 1/8, and so forth. In fact, this pattern continues all the way up. In summary, what we have actually done is, through the Fourier transform, rather than store a number in the 0 or 1 state of a qubit, we have stored that number in the rotation of a state around the z-axis. The unit of rotation is determined by the number of qubits we have. Here, with 4 qubits, we rotate by first 1/16 turns, 1/8 turns, quarter turns, and finally half turns. If we wanted to store the number 5, for instance, we will take 5 each and rotate each qubit by 5/16, 5/8, and so on and so forth. With this picture of the Fourier transform in mind, let's get to the maths. We want to find a way of constructing an N-qubit Fourier transform on a quantum circuit. That is, we want to find some sort of formula for converting from a computational basis state J into a Fourier basis state. This J is a decimal number, which technically is represented across n binary qubits. We will start by writing down our QFT formula. This big N is the total number of possible basis states we have. Let's convert this into 2 to the power of the number of qubits n we have, which is the small n. Then, we can convert our output state into the explicit binary notation. Instead of summing over the decimal values for k, we can sum over all the possible binary values on our n qubits. Note how each sum is over 0 or 1. We can then take out the sum out of the exponential to make a product. This sum has come from the conversion of decimal into binary for that k inside the argument. We can then turn this into a tensor product by noticing that our state is technically a tensor product across the qubits. By expanding this tensor product out, we can notice that we can bring in our sums as they don't depend on each other. Finally, we end up with this. This is an explicit expression for the representation of our initial decimal number j state in the Fourier basis. Each term in this tensor product is a state on a single qubit. As we can see, each of these complex exponentials encode that qubit's rotation about the z-axis, which we saw previously. Finally, let's take a quick look at the circuit that actually performs this Fourier transform. While this may look pretty intimidating at first, we actually have all the tools to understand what's happening. On the left, we have our decimal number x being converted into binary bits x1 up to xn. Then we can read the circuit from left to right. On each qubit, we perform a Hadamard followed by a chain of phase rotations controlled on every other qubit below it. As we can see, on the first qubit, we go from 2 up to n. On the second, we go up to 2 to n minus 1, all the way down until we get to the nth qubit, where we only apply a Hadamard. Each of the phase rotations is given by this matrix. We have actually already covered the intuition behind this circuit. The Hadamard shifts us into the x basis, or what I call the equatorial basis. Then, the giant bunch of controlled phase gates rotate us around the z-axis by amounts that depend on powers of 2. The reason why we need multiple such phase gates, rather than just a single one, as we mentioned above, is because our number is actually represented over multiple binary bits, rather than a single decimal number. As such, we need to, speaking loosely, join together each of these rotations by these entanglements. There are some other details that I've left out, such as the swap gates at the very end indicated by the connected crosses. This is because, as drawn here, this QFT circuit actually gives us the flipped qubit order, which we can undo with the swaps. Unfortunately, I will not be able to run through the circuit in detail, as we are now out of time. To the interested viewer, I strongly recommend you look into applications of the QFT, such as into Shor's algorithm or phase estimation. Hopefully this brief introduction to quantum computing and the quantum Fourier transform was informative. Thank you for watching.